Let me introduce our first speaker for today, Dr. Souvik Mahapatra, who is Professor for Electrical Engineering at the Indian Institute of Technology in Bombay. After his PhD in Bombay, Dr. Mahapatra worked for Bell Labs in the US before returning to India to continue his research at the IIT. His focus is on reliability of CMOS logic and flash memory devices, as well as the device circuit interaction. Dr. Mahapatra is an active writer and speaker, collaborating with different organizations like the IEEE or IEDM. And in today's talk, Dr. Mahapatra will talk about the early days of CMOS logic and the technology scaling, about innovations in materials and architectures, and about future challenges, how to scale further. So please welcome Dr. Mahapatra for his talk, Moore's Law, Past, Present, and Future.
Thank you, Michael. And I would like to thank ThoughtWorks for this wonderful opportunity. So let me try to share my screen. I'm Souvik from Electrical Engineering, IIT Bombay. I'm going to talk about Moore's Law. I mean, this is the topic of today's talk, but I am going to come from a slightly different perspective in terms of the technology side. Okay, I understand most of you are computer architects and software developers. Let me try to add a little bit of flavor from the technology side, and I'd like to, give you an idea of, how it all started and how the scaling went, and what are the different phases through which the technology went, and what are the challenges we are going to face as we move. So, of course, I understand there are quite a few students here, so I will try to give a little bit of introductory slide. We know that electronics is everywhere, and we can see all these great products that we use. And if you go into one of these products, you will see these printed circuit boards, and you will then see this kind of chips. And once you, probably that is all that you see if you open up your PC or your laptop. And if you then care to open up this package, you're going to see these modules. So these are actually the silicon chip that we talk about. And this is what is blown up here. So this is the part of this, silicon IC, or the integrated circuit chip. And if you look at it, it has, logic area and memory areas, and, mostly. And we can think of that, okay, it will have, say, the SRAMs, which is cache in your terminology, and of course the logic. Okay, and these symbols that you see are the transistors. So we know that in CMOS logic there are two sets of transistors we use. One is the PMOS that is connected to the power, and the NMOS that is connected to the rail, and to the ground rail. And therefore, we are going to see, essentially how these transistors developed over time, so that we could get the processors of today, and then we will see what we are having moving forward. So if you look at the transistors in few years back, it used to look something like this. So we used to call it like a planar transistor. I will try to give a little bit of background of how transistor works in a very, very superficial manner, so that you can understand the scaling and the Moore's law. And if you look at it today, this is, of course, the planar technology, which was in the earlier years. And since 2014 onwards, Intel introduced, and now everybody has introduced a technology which is called FinFET. So you can see this very nice fins, okay, and then there is this the transistor gates, and so on and so forth. So essentially, I'm going to talk about how the whole thing moved, okay, from very basic transistors to something very, very complicated, and where we are going to go now. So just to give you, I will just use two slides to give you a perspective of the scaling, or Moore's law. When we say scaling, we say technology scaling. So it is what is enabling Moore's law. So I will be using these terms interchangeably. So when we say technology scaling, if you look at the SRAM, or the cache memory, okay, from a 1980s technology. This was the area of the SRAM, and this is the layout. I mean, if you look at the chip from top, this is the layout of a 6-transistor SRAM having 1700 micron square area in 1980s technology. Now jump to 2014's technology, when the first FinFET, I'm sure everybody has heard about at least the technology or the name FinFET. So if I move to 2014's SRAM technology, you see that this is the FinFET. This is the SRAM that's showing there with the FinFET technology. And what is the size of this? If you go back to 1980s technology, and if you look at this thing, is just one contact to one of the transistors. There are 6 transistors, many contacts on those transistors, and that was one of the contact. And today's SRAM is this small little blob sitting over there. Okay, so you can see that there is about 20,000 times reduction in sizes. Okay, and you can imagine that because of the size reduction in a given silicon layout, you can put in, like a postage stamp, which is the size of a chip. You can put in so many transistors, hundreds of billions of transistors you can put in, and you can achieve all the functionality. And at the same time, you can have mobile applications, which means you reduce power and so on and so forth. So we are going to look at that as well. Now, the technology is scaling. We look at the motivation. Now, what is the motivation? The motivation is, I talked about technology from the transistor perspective. So I talk about, you scale transistor size, okay, and we will show that leads to faster switching, clock for some time, no more, and more transistors per area. I mean, this is valid, even very much today. Although, I will come back to that from a very latest perspective, what faster switching means today. Of course, we can have higher performance and more functionality. And at the same time, we reduce the supply voltage for mobile applications. So that today's mobile phones can do much more than yesterday's PCs. And more importantly, it's a huge reduction in cost per functionality. So I was looking at some place that in 1975, a transistor cost, and in today's a transistor cost, is about 1 billion times less, or even more. Okay, per transistor cost is less, and therefore you can pay the same amount of money and get that many more transistors in your chip, and therefore you can think of all the functionality that you can do. So just for the students to give you a perspective, I don't know how many of you have used this. I certainly did in my school days. Then of course, in 30 years you go from this PC to this PC. Of course, you can see that you can get much more functionality, much more power in your hand now, that you used to have even say 8 years back. So therefore, this is all about Moore's law, and how Moore's law enable this technology scaling, and how we can have more and more powerful devices. So scaling enables affordable high performance electronics, and therefore there are two things important. Of course, high performance is important, low power is important, and most important is affordable. Unless it is affordable, this is not going to go. So with that little bit of introduction, I'm going to talk about the main topic. I'm going to talk about 3 main things. So I have to introduce the CMOS transistor operation in a very, very nutshell. I hope you would be able to follow what I'm saying, okay, and talk about conventional scaling. So this is called the Dennard scaling. And then we are going to move to this alternate scaling. And therefore, we are going to talk of innovation in materials and structure. And we are now in this range, and we will see how we are moving forward. And towards the end, very briefly, I'm going to talk about reliability. So transistor aging and breakdown, like we humans, these transistors, and therefore chips also age and they break down, and therefore we need to see what causes this, and that's precisely my area of work. So I will just briefly introduce that. All right, so this is the transistor operation in a very nutshell. You can think of this as a channel. This is a silicon, and this is a source and drain. Okay, these are the two. So this is I'm assuming familiarity to some little bit of semiconductors. So suppose this is p-type silicon and the source and drain are n-type silicon. So this is called the NMOS transistor. If you have an opposite thing, it is called a PMOS transistor. And there is a gate, okay, which controls, turning on and turning off this channel. And the gate is isolated from the channel by something which is called the gate oxide. So this is an insulator. So this is a gate, which is a, say, it's a metal. And then these are all semiconductors. So, how do I understand transistor? So I can understand transistor by looking at an electron sitting at the source and the channel, which is as a barrier. Okay. And when I have put in all voltages, source, gate, drain, and bulk, all voltages 0, this is what it is. And the electrons is a barrier, it cannot go. Now what happens is if I apply a drain voltage, okay, when I apply a drain voltage, what I do is I lower the drain side of the barrier, okay, but still the source side electrons is a barrier, so it cannot go, the gate is still off. But then when I apply a gate voltage, when I turn on the gate voltage, this barrier is now lowered and therefore the electrons can go. So basically this is a gate control switch, so I can control the flow of electrons from the source and drain by turning on or turning off the gate. So you can think of this as a pipe which is carrying water and the gate as a valve. So I can turn the valve on, water will flow. I can turn the valve off, the water is not going to flow. So this is what transistor is in a very nutshell. Now, of course, if I want to look at the current voltage characteristics, so what I do is I try to measure the current in the drain. I ground these two and I apply a gate voltage. So I'm plotting the gate voltage here and I'm plotting the drain current here, and I'm plotting the drain current in a log scale, okay, which means that this is, every tick mark is say 10x, that's how it is increasing. So what I see is that the current looks something like this. So first it, when I turn the gate voltage from 0 to on, it increases exponentially, then it hits a knee, and above the knee, it varies linearly. So if I want to look at this knee, where the knee happens, it is called the threshold voltage or the VT. And above this knee, we call the transistor is on, and below the knee, we want to make the transistor off. Of course, in an ideal switch, I want to have it just like a sharp switch, but that never happens, and this has important implication. So, the on current per width of the transistor is given by, this simple looking formula. So, where this Cox is the gate capacitance, okay, the W is the width, okay, and what you have is this capacitance times the voltage. So VG is your gate voltage, VT is your threshold voltage. So this is your channel charge, CV is your Q, channel charge, and VD is your drain voltage, L is your length. So this is the lateral electric field, okay, and mu is your mobility. So basically your current is given by charge, mobility, and field. This is simple physics, okay, and we will look at how these terms impact when we talk of Moore's law. Now, the carrier mobility and gate capacitance influence the on current. On the other hand, if I look at the off current is because of this, emission of these electrons over the barrier, and this the off current, of course, goes exponential, okay, in gate voltage. So this is something important to remember. Now, what is the motivation of MOSFET scaling? What we do is we look at that this electron has to travel from the source to drain, and if we can define a transit time, if the velocity of the electron is v and the length is L, so the transit time is L by V, and the switching speed is 1 by transit time. So originally what people thought that if we scale the length, that I'm showing here, what we are going to achieve is, I'm going to have a shorter transit time. And if I define the delay tau as CV over I is your drain current, okay, and your CV is the capacitance of the next load that you're driving, and V is your voltage, okay, and the drain current, is inversely proportional to the length. So if you reduce your length, your current goes up, your delay goes down, and you can have faster transistors. So that was the original motivation of Moore's law. Now, the problem is there is no free lunch, and therefore what happens is we have to deal with something which is called the short channel effect, and this is where Dennard scaling come in. So, I'm looking at this transistor and I'm looking at this barrier to the electron. So, when I apply this, gate and drain voltage, okay, the drain side pulls, the drain voltage pulls the drain side, and then the gate voltage lowers the overall thing. And most importantly, the drain does not impact the, the no impact of the drain on this side. Okay, so this side, this turning on and turning off this side is purely controlled by the gate. But if I look at the short channel transistor, okay, I look at the same barrier again, and I apply a drain voltage, okay, and what happens is, whatever barrier I want to reduce, a part of the barrier is reduced by the drain, because you can see from simple electrostatics, the drain is now sitting closely to the source. Okay, and therefore, although you'd like to control this barrier, turning on and turning off by the gate, the drain kind of comes in and fiddles with it. Okay, and this is called the drain induced barrier lowering in our terminology, or you can simply think of is as a short channel effect, wherein ideally I want only the gate to turn on and turn off the transistor, but now the drain is also fiddling in, and that causes all sorts of problems. Now, what are the problems that it can cause? Okay, there is a loss of gate control. So I'm getting a less ideal transistor. So what we like to do is we would like to, of course, shrink the distance between source and drain, but at the same time, I would like to reduce the source drain interaction. I need to increase the gate control. So if you simply think of this as two capacitors connected from the gate and the drain, I would like to reduce the impact of this, and I'd like to increase the impact of this. So that is what I'd like to do. And this is all Dennard scaling is all about. So to achieve that, what we do, okay, so this is the traditional solution of the Dennard scaling. So the first thing is you say, hey, if I want to have more gate control, why not I reduce the gate oxide thickness? If I reduce the gate oxide thickness, gate comes close to the channel, I have more control. Good. The second thing is, you say that you reduce the length physically, but you want to increase the length electrically. So what we do is it's those who are familiar to semiconductors, that we dope the semiconductor N-type or P-type. So in this case, the P-type substrate and N-type source and drain. So if I locally increase the doping, the P-type doping, the fields are not going to penetrate that much. Okay, because the field penetration is inversely proportional to the square of the doping, roughly speaking. So, if I increase the doping here, it is not going to go. And then the third thing is, we say that, look, the culprit area is this, because this is the place where the drain and source are going to talk the most. This is farthest from the gate. And therefore, what I do is I need to shrink that as well. Okay, so this is the classical Dennard scaling, which says that, okay, you scale the channel length, you scale the gate oxide thickness, you increase the doping, you reduce the junction depth, and at the same time, you reduce the supply voltage also. And this I'm going to come in a moment, and you are good to go. And that is what, the Dennard scaling era was. So if you look at this Moore's law, for every 2 years, the feature size scales by 0.7x, the transistor count goes by twice. And you can see that from the 1970s, when the feature size were about close to a micron, and then it kind of continued to scale. And of course, it kind of continued to scale a little faster, and something happened. I will talk about that part later on. Okay, and so this is the feature size, which continued to scale, and this is the transistor count. Okay, so this is the time when I was born. Okay, and this was the Intel's first processor, and now we have hundreds of billions of transistor in the processor. So this is how the feature size scale, and I said that the oxide thickness, that thin insulator that I talk about, that is also very important. It used to be like hundreds of nanometers in those days, and it is about a nanometer today. Okay, so this is how it is scaled. And of course, if you remember those days, the logic used to be 5 volt. Now it is like less than 1 volt. Okay, and you see that, of course, that we need to do, because if I look at, say, a range of scaling. So this was 1 micron, and this is 20 nanometer. So in this, if I see that the channel length is scaled by 50 times, the oxide thickness can only be scaled by 10 times. I will say why. Okay, and the supply voltage can only be scaled by 5 times, and I will say why. And you can see that, therefore, the dimensions are scaling much faster than the voltages, because there are certain reasons why you cannot scale the voltages. An electric field inside the device, is going high, and that causes all sorts of problems, including the reliability problems, which I would like to touch upon later on. So that scaling leads to the power problem. So you remember we talked about this kind of an IV curve, okay? And when we look at the scale transistor, okay, you can see that you can scale things, you can reduce the VT and all of that. But what happens is your on current, changes only linearly, okay, provided the mobility does not go bad. And I will talk about that, this can also happen. But what happens is the off current goes exponentially high. So you have, when you scale, you increase the on current linearly, which you want, because this is going to give you a performance, but this is going to give you your power, okay? And you want this not to increase much, but unfortunately, the off current increases exponentially, on current increases linearly. Okay, and therefore, if you look at the dynamic power versus static power, or the active power versus the static power, you can see that in this range, the active power, is kind of going up like that. But now, the subthreshold power or the off-state power is almost equivalent to your on-state power, which means that you spend as much in not doing something than doing something. Of course, people use intelligent power management to handle that, but this is an aspect of the brute technology scaling. So what are the limitations of traditional scaling? Because you cannot, that power, there is of course a problem, and the other problem is you cannot scale the threshold voltage, because this is an ideal 60 millivolts per decade at room temperature. This is what dictates this slope, okay, that you cannot turn it off faster, you cannot turn it off like that, and therefore you cannot keep it very close, because the leakage power is going to go, and therefore you cannot scale your supply voltage as much as you want, because you have to maintain the overdrive, otherwise you are not going to get the performance. And as a result, your electric field is going to go high, because as I said, that the supply voltage scales only say 5 times, your channel length scaled 50 times. So your electric field is going to go up by 10 times. And we know that the mobility, okay, reduces as the electric field is increased. So in this device, you have been doing everything expecting this is not going to change. But what happens is this has reduced. So by the end of 90s, early 2000, people got stuck with this. And this is when the Dennard scaling stopped, and people made the first innovation is they use, stress liners to boost the mobility. Okay, so this is the first inflection point when, till, from 70s all the way to late 90s, early 2000, okay, then there is the first thing. So I'm going to now move to the alternative scaling and talk about what people have done. So the first thing, you can think of that this Moore's law I was talking about. So this is the conventional scaling. Early 2000, it has stopped, and the Dennard scaling, and then the innovative scaling has started. So new materials and things like that. So as I was talking about, that scaling, increases the electric field and reduces the mobility. Okay, and therefore, if you do nothing, it is going to reduce your drain current. You want to achieve higher drain current, but it actually goes the counterproductive way. So what you do is you introduce stressors, mechanical stressors, to increase the mobility. Of course, without going into detail, I can talk about that there are 2 things that you do. One is you put in a sort of a material on top of the transistor, which is going to either push the gate or pull the gate. Okay, and the other thing that you do is put in different source drain material. So for PMOS, what you do is you put in a material that is going to push this towards each other, the source and drain. It squeezes, and also this is normally silicon. The channel is silicon, but you use silicon germanium source and drain, and this is a bigger lattice than this, and therefore it gets squeezed. So imagine sitting a very, so to say, kind of a thin person sitting in an airline middle seat, in the middle of 2 very healthy person, and you can think of, it is a compressive stress. And the other thing for NMOS, what you do is the opposite. You put in a liner that is going to pull this, on the other side. You can think of now the healthy person sitting in the middle and the 2 thin persons sitting on the other side. So you're kind of pushing them out. Okay. And of course, people have tried to do silicon carbide source drain, but that does not work. So with this mechanical stress, you can do the boosting. So I'm not going to go in very much detail. So there are ways of doing it, and fortunately both adds up. Okay, so you can, this is the technology that IBM came up with, the tensile nitride and the compressive nitride. And this is the technology that Intel came up with, the silicon germanium source drain. And now they cross-license and everybody uses everybody's. So you put both and you get the boosting. So, if I plot this kind of a plot, so what I'm plotting is I'm plotting the off current here, that when you put a 0 gate voltage, this is the current you get. By the way, 0 gate voltage current is never 0, and this is the on current. And you can see that, this is when there is no stress, and this is when there is a mechanical stress applied. So for a given off current, you see higher on current. So this is how you can boost performance. And that is what the first thing that you have done. So the next thing that you have done is I talked about the gate oxide scaling. So the limitation to gate oxide scaling is if you reduce the gate oxide, okay, for every, below 30 angstrom, today it is about 10 angstrom. So for below 30 angstrom, if you want to reduce this gate oxide, which is silicon dioxide, you have a gate leakage current increase by an order of magnitude for every 2 angstrom reduction in the oxide thickness, which means that although you want your current to flow like this, you're going to get a leakage component, and this leakage is going to add up to your standby power. Okay, and therefore what people have done is they have used a higher K material, okay, replace the silicon dioxide first with silicon oxynitride, and now with the metal gate high K technology to reduce this leakage. Because if you use a higher K, you can have a higher physical thickness but lower electrical thickness of the capacitor. But what happens is higher K are poor quality. So what you do is you keep a thin SiO2 layer and then you put the high K. And what happens is you can therefore reduce the gate leakage. And if you want to further scale the gate stack, what happens is if you do the IL scaling, your leakage goes up by the same amount, 10x, every order of magnitude increase for every 2 angstrom reduction in the thickness. Whereas if you want to do the same for the high K, it is double the rate. So, high K scaling is not something that people say. It is about 17 angstroms today, but the IL is about 7 angstroms or 8 angstroms. People might have some play, over there to do. Okay, so this is what the plot from Intel. So what happens is you can see that the gate oxide thickness was scaling, okay, and the leakage was going up. And at some point, the gate oxide thickness could not scale because they could not afford to have a lot of gate leakage. And then the high K metal gate technology came in at 45 nanometer for Intel, 28 nanometer for everybody else, and the gate oxide thickness could be scaled, and the leakage could also be reduced. So if you remember this plot, okay, you can see that over these different technology nodes, you can see that pretty much here the leakage power was lower than the active power, but in this case 20 nanometer they are almost the same. So therefore people have if you do not do the high K, this is the estimation. So of course you have to move to the high K technologies. So the last thing what people have done is, see, the problem is that this source and drain talks to each other, okay, and therefore one option is to not have a very deep source drain. So the ultra thin body SOI or silicon on insulator or fully depleted SOI technology is one technology that some companies like STMicro and Global Foundries are pursuing. Those are of course not mainstream RF, and those applications this technology is good. But what most people have done is, they move to FinFET. So basically, rather than having the channel that looks like this, you kind of twist the channel like this, and you flip the channel like this, like a fin. So this is your source, that is your drain, and you wrap the gate on 3 sides. Okay, and this is what it is, and this is what the latest technology is. And what you are going to get, say, sometime 2024, 2025, as of now, okay, is something which is called the nanosheet FET or the ribbon FET. You may be hearing a lot of this buzz where these are the channels which looks like this these sheets, and then you have the gate going all over, And if you kind of try to look at it, it's kind of wrapping all the sheets. And therefore, so this problem of the gate being far away from this part is not there, because if you're wrapping it all around, so you're going to get better performance. So this is in, so this is in production, this is in production, this is going to be future. So, I'm not going to go through all this detail. The slide is going to be there. So basically, I want to say that we want to see, how efficiently we can turn off the transistors. The subthreshold slope, lower the number is better, and how much less the drain-induced barrier lowering is, okay, the less the better. So you see that if you go to nanosheets, okay, these numbers sort of go down. And I will not go into all these details in this. So basically, this is how an Intel FinFET look like. This is a 20 nanometer structure, and I want to just show that all that I talked about are, Intel has introduced, say, at 90 nanometer the strain technology to increase mobility. Then at 45, so you introduce something, then you mature it over 2 technology nodes. Then at 45 nanometer, they introduce the high-k metal gate technology to cut down the leakage. And then at 2011, they introduced FinFET to cut down the short channel effects. Okay. And now moving forward, before going there, I want to say this one important thing is that if you have not done this innovative scaling, so at 130 nanometer node, suppose all that you want to have, it is 1. At 90 nanometer node, it is going to be this much coming from classical, and strain is giving this much. So at 65, this is what you are going to get the classical performance. This is you are going to get from the strain. Moving to high-k metal gate, okay, is going to give you this additional performance. Okay, and then moving to tri-gate is giving to this additional performance. And you can see that if you would have stuck with the Dennard scaling, your performance would have actually stayed stagnant, or actually go, it was supposed to go down a little bit. So you get all these, additional performance, okay, because of all these, this non-Dennard type innovations, mechanical strain, high-k metal gate, surround gates, tri-gate, and eventually surround gate. The problem is this, okay, you can see that 2011, Intel introduced the 22 nanometer FinFETs, okay, where the channel length was 26 nanometer. 14 nanometer FinFET was introduced at 3 years down the road at 2014. Okay, you scale the channel length by 6 nanometer, and at the 10 nanometer, it was delayed, and 2018, 2019 maybe. Okay, when it was sort of came into play, and you can see that you hardly scale the channel length by just 2 nanometers. Okay, so this is a problem, and then things are slowing down. There are lots of issues, and the possible way of moving forward is gate-all-around nanosheets. And if you look at the transistor density is going very high. So 10 nanometer has in 1 mm square area 100 million transistors. So depending on the size of the chip, you can imagine how many transistors you will have. And because we could scale the transistor size, we could scale the size of the core also, and therefore you can see that this entire, the logic, IO, and SRAM, this entire thing is going down, and therefore in a given total chip area you can have multiple cores. So you talk about multiple cores, because of the scaling, the size is reducing, and you can put in multiple cores. So that's what the scaling is. How much time I have?
We have a couple of minutes left, about 5
Okay, so I will just quickly flash on the aging and breakdown. So as we scale, I talked about that the voltages don't scale as much as the dimensions, and therefore electric field goes up, and therefore we have a reliability problem. So reliability, we talk about a bathtub curve. So this is a failure rate versus time. So there is this one part which we call the infant mortality. This is mostly process defects which gets matured over time. And then there is one time when there is this random failures. Things can happen randomly. Okay, but we are interested in this part of the towards the end of the product life. This is the wear out failure or the aging. Okay, and this determines that how long, when you create a technology, how long it is going to go. So So these part is solved by production issues and yield improvement. And this is where we do the reliability assessment. So, there are different sorts of reliability. You can have package reliability. You can have die-to package reliability. Even if you look at the chip, you can have the reliability of these metal layers. You can have the reliability of this back-end intermetal dielectric. And of course, you can have the reliability of the transistor. Okay. And, this is, of course, one of the most crucial thing. If transistors don't work, nothing else would work. And this is where the most of the technology, goes in terms of trying to fix the transistor so that it can perform. And at the same time, it can deliver the performance. Of course, you need to make sure that your metal interconnects and all these are, not putting any performance bottleneck, and they are also reliable. So, so as I said, that the feature size scales more than the supply voltage, higher electric field. So I talked about the gate insulator, and what happens is in the gate insulator, there are appearance of defects, and those defects get charged up and changes the performance of the device over time. And there are two things that can happen. One set of thing is a gradual shift or aging or slow performance degradation leading to failure in long time. And there is sudden failure or breakdown. These two things can happen. So as a result, what do you have? Failure of circuits and products. And so reliability assessment is you need to identify the worst case aging or the failure mode. Okay, you need to do that because there are many times multiple processes, failure processes in play. And then what we need to do is, of course, these failures happen a long time. You cannot be testing that long time and then come back 5 years down the road and say, hey, this is good, this is bad. So what we do is we accelerate the degradation and test the impact. And we want to make sure that when we accelerate it, nothing else happens. We are accelerating the one we want to accelerate. And then what we do is we build models and methods to project, these accelerated short time tests to the end of life at use profile, use condition, and want to make sure that whatever your use profile is, this technology is going to qualify. Okay. And if it does not, then we have to do two things. Either have to go and change the design or tell the designer that, hey, you cannot use this much overclocking. Overclocking is something happening now. Okay. And of course, at the same time, we have to go fix the process. So, as I mentioned, overclocking, that we talked about this, clock, and Intel's latest offering, Alder Lake, which is right now out, and they say that they are overclocking, and nominal is say 0.9 volts, and they can overclock up to 1.3, 1.4 volts. So, to get the performance, some cores will overclock for some time to give you the performance that you need. Okay. And then, of course, some other cores will overclock. And so these kind of reliability issues are going to be very, very important. So that's my conclusion. So continued scaling of CMOS transistors resulted in high performance and low power products. Of course, its industry has done collectively a phenomenal job, and Moore's law is continuing. We shall see when it is ending. Maybe every 10 years we speak about Moore's law ending, and the industry has pushed it. So we will see when it goes to end. Innovation in material and architecture, kept it going. Reliability is an important thing. It's one of the most important thing. And the performance reliability co-optimization is coming up as a very big area. So those who are aware of the term DTCO, design technology co-optimization, there they talk of performance, power, and area optimization. But we are working with some companies to make sure that we can get the reliability not as an afterthought, but also during this process development, so that this whole thing can continue. So with that, I would like to thank you for your attention, and any question that you have, I'll be able to take.
Thank you, Dr. Mahapatra. For me, who didn't study electrical engineering, was great to start this day with a bottom-up approach and explaining the history of the scaling, and understand from your conclusion that you believe that Moore's law will still hold true. Is it with you mentioned some of the scaling and the alternative scaling method. will this law still hold with the methods you presented, because some of them were still in the future, or does it need another breakthrough, another topic, how to scale?
It's a very good question. So when we talk about the new architecture, the ribbon FET, that's going to happen in another couple of years. So maybe, or maybe a little bit more. By 2024, 2025, that is going to come. I do not know what is going to happen afterward. So that is going to stay as the technology, is concerned. Now, if you can improve reliability, what is happening today is you see a reverse scaling of the supply voltage. So as I just mentioned, for overclocking, you are doing a reverse scaling of the supply voltage and you are getting some performance out of it. The other thing of scaling is, these multiple cores, and that is happening. You are having many cores. So, to an end user, who would like to have more performance at a lower power per performance, you can achieve it by this scaling or simply having more cores, and you can have, going forward these things. Of course, people are also talking about innovations in different type of devices. That the biggest challenge that we have, the biggest challenge is not having super fast transistors, but the latency between the logic and the memory. You kind of go back and forth in terms of data between the logic and the cache, and that takes a lot of effort, a lot of power and delay. So if you can put a memory next to the logic, so people are talking of newer devices that they can put in next to the logic, and therefore can create a hierarchy in the memory, so that you can, the data that you want to fetch very quickly, you keep it next to the logic. There's those specialized memory next to the logic, and something that you need a little bit later, you put it in the SRAM. Something you need even later, you put it in the DRAM. And then, of course, nowadays people are also storing this data in their hard drive and pulling it back during compute. This, there was a lot of this debate about whether the hard drives are getting burned out, like the solid state drives are getting burned out or not. I mean, you have this Optane memory which sits between the DRAM and the hard drive. So there are lots of these memory hierarchy. I just only talked about the logic devices, but also memory side you have to look at, because everything together gives you the system. So this logic memory latency is something that people are working out as well.
Thank you so much. And I think we're going to look into different aspects of scaling further, rather than the transistor. Thank you. Looking at the time, Ashok, you want to introduce our next speaker?
Absolutely. I think just Dr. Mahapatra's talk just reminded me of everything that I distant past learning about P-type and N-type semiconductors. But yeah, it was just fascinating refresher. But actually, just as you see in the chat as well, talking about looking at that fundamental level, what are the challenges of scaling and how we are overcoming that. So yeah, thank you for that.